following functions are multilinear. Okay, so here's the first function, so it's delta, which is so it maps, so it goes from 3x3 matrices of a field F to the field F, and the definition of this function, well, basically we just take the matrix, right? We just take the matrix and assign to it, well, so say matrix A consists, so it's 3x3 matrix, right? So it consists, say, of the entries A11, A12, and so on. You can just fill it in. And basically, okay, so what this function does, it assigns to each matrix the respective entry. Well, the entry is the position 1, 2. Okay. Now, okay, so how does one attack this problem? Okay, so here basically the question is just about to check the properties of being a multilinear function, right? So, and let me remind you that okay, first of all, this function is defined on space of 3x3 matrices, right? What does it mean? Well, it actually means that here M3 of M of F is considered as a row space, right? So let me write it down. So it's basically consists of all matrices. Let me still keep it 1, 3, A21, A22, A23, A31, A32, A33, right? So all such matrices, right? And well, be careful that, okay, so here we'll look at the rows. So the first, the second, and the third rows, and each of those rows is our V. It's a copy of our V, right? So indeed, one may think about this delta is V times V times V to F, right? So this is the, again, this is the first row, the second row, and this is the third row. Yes? So now, well, if you remember the definition of a multilinear function, what does it mean? Well, it means that, well, basically we want to check if you want a delta to be multilinear, that you want to check that delta is a linear transformation with respect to each row, right? To each row, to each vector space, to each coordinate, to each vector, right? So what does it mean? It means that we look only at this row and we fix the other rows. So other rows are kind of constants. So we fix them. And then we look at only the chosen row and check whether this function restricted to that row is a linear transformation. Okay. So for instance, well, let's just look at, so let look at delta restricted to the first row. So what does it mean? It means that, well, if we just look at this matrix, we just only think about those A11, A12, A13 as variables, and all these other entries are like constants, so they're fixed, right? Now what's the function? The function is just A12, right? Again, so this is one vector, this is say V. So if you wish, you may also think about it like delta of V is of this vector is defined to be A12, right? Okay. Somehow you don't care about the other entries. You fix them, Okay, so now the question is whether it's a linear transformation. Of course, the answer is yes in this case, right? Why? Because if I just apply my sort of restricted delta to the sum of two vectors, what's this? This is just delta of, I'm just copying this vector, right? Okay, say for instance, this is A11, A12, A13. Maybe I should put one somewhere. Let's put, okay, so that's, so okay, let's say V1 is A11, A12, A13. And say V2 is say A11 prime, A12 prime, A13 prime. Then, well, if I substitute, I get A11 prime, A12 prime, A13 prime, right? And then if I expand, what do I get? I get A12 plus A12 prime, right? And that's precisely what I want, because this is exactly delta of, well, delta of V1 plus delta of V2. Yes. Again, I add these two vectors here using the standard rule, the addition rule, and then just look at the second coordinate, and that's just the sum of, and that's just the sum of these guys. Okay. So that's fine. And in the same way, you can check that this respects the scalar multiplication. Okay, good. So now, what about now? So now let's look at the, so now we'll look at delta restricted to the second row. What will happen in this case? Well, okay, so now what we do, again, we just, we only look at the second row and we fix all other entries. And then what's our function? Well, our function, well, actually there's this one entry here, which is a constant. So it's a constant, we fix it. And this delta, what it does, it maps any second row to that constant, which is fixed, which does not depend on that second row, right? Okay, so now, well, if we would like to check that whether this delta is a linear transformation, restricted, second row, then we will realize that it is not a linear transformation, is not a linear transformation. Because a constant function, I mean, a constant function, right? If this constant is non-zero, but this is the case here, I mean, because it's a general matrix, is never a linear transformation, right? The linear transformation has to preserve zero, for instance, right? So it's not a linear transformation as delta of zero is not necessarily zero. Well, this is what this is. Yeah, it's not necessarily zero. Okay, but that means that it fails this test, right? The multilinear test. So it means that with respect to the second row, it is not, so it is not a multilinear function. So delta is not a multilinear function. Okay, so that was question one. Now question two. Well, let's look at the following delta from M3F to F, all the same description, However, now what we do, okay, let me slightly change it. I mean, because you anyway can see the solution. I mean, you can just read the written solution, right? Let me do kind of extra example. Instead of the sum of squares, let me take, say, let me take this A11, well, A22, and A33, the product of, say, diagonal entries. Okay. And now the same question, whether it's a linear, whether it's a multilinear function or not. Okay, so now we again check for each row, right? Okay, so first row, for the first row, what this delta does. So A11, A12, A13, then there's constants. And then what it does, well, it sends this matrix to A11 times A22, A33, which are constants, right? So these are two constants. And this A11 varies. I mean, that's a kind of variable, right? Okay, so now basically what does it mean? It means that, okay, so, well, if you wish, you can think about this delta as a vector. So I mean, it is defined for this vector, right? And what it does, it just maps this to the first coordinate times some constant. Well, if you wish, you can also say denoted by C, right? So it's a constant. And of course, we all know that this is an example of a linear transformation, right? So if you take a vector and the multiple of the first coordinate, yes, this will be a linear transformation. It's pretty easy to see. So is a linear transformation. So it's fine for the first row, it's fine. Now, what about the second row? What about the second row? Well, indeed, you may realize that it's kind of symmetric, right? It doesn't really matter because it's a product of all diagonal entries. So indeed, well, one can see that that's okay, right? So that's also a linear transformation. Again, you just fix the second row and you send it to this A22 times the product of other two entries, which is a constant, right? Which does not change. So it's again a linear transformation, and as well as the third row. And since all of them are linear transformations, so delta is a multilinear function. Okay. So this finishes question 2. Is there any question? Any question? Okay, then I'm going to the next. That's a question 3. Of the assignment form. So here we have, so let R C to denote the vector space, of all polynomials with real coefficients of degree less or equal than 2, and particular. Okay, so there was a question, let me address it. When applying the delta function with respect to the first row, I wrote out the entire matrix. Yes, it's fine. It's fine if you write down the entire matrix. However, yeah, you can maybe just like put, I don't know, just stress that the rest, you see, the rest of the matrix is fixed, right? So it's a constant. Yeah, that's okay. Okay, good. So now, right, coming back. So suppose that we have a vector space of polynomials of degree at least 2. Yeah, so let me remind you that this vector space consists, well, another way to write it down, so just consists of all polynomials of this form, TB plus C, so T square C, if you wish, where A, B, C are real coefficients. Well, doesn't matter if you write TB or BT, it's commutative. Okay, now, well, let C be a linear operator. Be a linear operator. Defined by t applied to a plus bt plus ct square is c plus a plus b t square, for instance, right? Now, well, the question is, okay, so first compute the eigenvalues of t. Well, let me just do it case by case. So first question is compute the eigenvalues of t. Okay. Okay, so first of all, what we need to do in order to compute the eigenvalues, well, we need to write down the transformation matrix with respect to the basis alpha, right? So what's a basis? Alpha is the standard basis, and in this vector space of polynomials, we all know that the standard basis is given just by powers of t. So that's a standard basis, right? And now, well, we just need to write down the matrix. So what's a matrix? How do we write down the matrix? We take the basis vector, right? We take the basis vector. Say first we take 1, yeah, that's 1 here. Then we apply our t, right? And then see what, I mean, which vector we will get. Okay, so if you just substitute, here, I mean, a equals 1, b equals 0, and c equals 0, what do I get? I get clearly, okay, let me write it. A plus bt plus ct square. So a is 1, b is 0, c is 0. That's exactly 1 here, right? And then what do I get? Well, I get clearly if I apply, because that's t applied to this, and that's what this is c plus a plus b t square. But now c is 0, b is 0, and a is 1, so I get t square, right? So I get the vector, what vector I get? So coefficient at constants is 0, at t is 0, and then t square is 1. And then similarly, I compute t applied to t, small t, and then I'll get this vector 0, 0, 1. And finally, when I apply it to t square, what do I get? Well, I get 1, 0, 0. So this is my matrix, right? Okay, so now, so we want to compute eigenvalues. So what do we have to do? Well, we need to look at characteristic polynomial, right? So what's a characteristic polynomial? We need to take this matrix and subtract from it x times, well, lambda or x lambda times the identity matrix and try to compute its determinant, right? So what's this? This is just the determinant of what? Of this matrix minus lambda times the identity matrix. So it will give me what? Minus lambda 0, 1, 0 minus lambda 0. And here I get 1, 1 minus lambda. Yes, and then it is pretty straightforward to compute this determinant. So I leave it as an exercise and just write down the answer. So what's this? This is lambda times 1 minus lambda times 1 plus lambda. And from this expression, we see that the eigenvalues are lambda 1, or just roots. They're just roots. So lambda is 0, that corresponds to this factor. Then lambda 2 is 1, and lambda 3 is minus 1. So those are eigenvalues. Well, second question. Second question is, we would like to describe the eigenspaces, right? So, or another way, so find bases for each of the eigenspaces of T. Okay, so there was I'm coming back. So there was a question. Could you please explain how you got the vectors in that first T matrix again? Okay, let me go back. Back. Here, you mean in this matrix? You mean in this matrix? Okay, good. So what do we do? This is a transformation matrix, right? With respect to this basis. How do we write down the transformation matrix? We just, I mean, you see each column of this matrix. So this is just what? This is just T of 1. The second column is T of T. And then the last column is T of T square. So what do we, how do you get these columns? How do you get these columns? You just substitute. Well, look here, for instance, I want to compute what is T of T square. What is T of T square? What do I do? I just put here 0, 0. I need to get T square, right? And here I need to put 1. Okay. Yes. So my A is 0, B has to be 0, and C has to be 1. Then I just substitute this A, B, C here and see the result and get the result. Okay. Right. Okay. So what do I get? If I substitute, what do I get? Which polynomial do I get? So A is 0, this is 0, because this is 0. Then B is 0, this is 0. And then C is 1. And that's exactly means that the result is 1 times 1 plus 0 times T plus 0 times T square. And that's exactly 1, 0, 0. See? 1, 0, 0. Okay, so just write down the coefficients. Okay, coming back to that question too. So what we would like to do now, we would like to find the basis of each eigenspace. Well, actually, before doing this, look, I mean, there are three eigenvalues, and the dimension is also 3, right? Because it's 3 by 3 matrix. So meaning that each eigenspace must have dimension. Well, there's no other way. It must have dimension 1, right? Okay. So first of all, look, I'll observe that each eigenspace must have dimension 1. Because all those eigenvalues are different, right? And I mean, whenever you have an eigenvalue, there always must be an eigenvector by the very definition. And this has to be a non-zero vector, right? So meaning that, well, there's no other way that to have 3 different eigenspaces, and each of them must have dimension 1. It cannot have dimension more than 1, because then the total dimension will be, it's a sum, right? Then the total dimension will be 4 or more, but it's not the case, right? So it has to be 1 each. So so basically, if you look at the bases for each eigenspace, we just need to provide 1 vector for each. Okay. Well, let's just how do we find the basis? Well, we just substitute again, right? We'll say take lambda 1 is 0. Then what is E lambda 1? Well, this is a null space, right? This is a null space of this matrix after substituting lambda to be 1 to be 0. So let me put this as a null space of, now I substitute, instead of lambda I put 0. So 0, 0, 1, 0, 0, 0, 1, 1, 0. And well, now I can just simply solve it. Or I can also write it down like this. So just set of solutions of the equation 0, 0, 1, 0, 0, 0, 1, 1, 0 times V equals 0. One just needs to solve the system of homogeneous equations and write down the general solution. And then one will see that the solution is of this form always. Say, I don't know, say you need some parameter, right? Probably. So I don't want to use t. Let me use say x minus x0, where x is from R. That's a general solution of that system of equations of that homogeneous system. And well, I see that the basis vector here is 1, minus 1, 0, right? So this is my, yeah, so this is, right. So this is a whole set of solutions. And well, I can take as a basis vector, I can take this V1 to be just 1 minus 1, 0. Yeah? But don't forget that this is a polynomial. So we still must express it as a polynomial, right? And this would correspond to 1 times 1 plus minus 1 times t plus 0 times t squared, which is 1 minus t. And similarly, I will, okay, so let me just mention. So lambda 2 is 1. So for that one, E of lambda 2 is the null space of which matrix? So again, instead of lambda, I have to substitute 1. So I get minus 1, 0, 1, 0, minus 1, 0, 1, 1, minus 1. And then I can solve it and just write down the general solution of that homogeneous system. And then what I will get something like this, x0, x. And then again, I can just write down the vector, which will be 1, 0, 1. And so this would correspond to the polynomial 1 plus t squared, right? So it's 1, 0 at t, and 1 at t squared. And finally, the same arguments gives you expression for the last remaining basis vector, which is 1 minus t squared. So the answer is 1 minus t, 1 plus t squared, and 1 minus t squared is the collection of basis vectors for each of those eigenspaces, right? By the way, from this expression, from this, you can immediately deduce the answer to the last question. The last question asks whether T is diagonalizable. And the answer is yes, T is diagonalizable as, well, there's several criteria, but here one can use just a very direct one. Namely, if you look just at this set, you realize that they indeed form a basis. They indeed form a basis of the whole space of polynomials, right? So meaning that as this minus t, 1 plus t squared, 1 minus t squared forms a basis. And this is indeed one of the major criteria, right, for being a diagonalizable. Okay, so here was a question. So we should say the basis for E lambda 1 is 1 minus t rather than the row vector. Yes, exactly. Yes. You can, I mean, it's not good to sort of to stop at the level of row vectors. You still have to express them as polynomial, the criteria for diagonalizability. For instance, well, it's very important to look at the criteria which relates, say, the algebraic multiplicities and geometric multiplicities, right? So remember that the criteria for the diagonalizability tells you that so whenever you have the matrix is diagonalizable if two conditions are satisfied, right? Well, of course, here you also need to know the basic properties of eigenspaces. For instance, whenever you have an eigenvalue, there is always an eigenspace of dimension greater or equal than 1, right? Saying the sum of dimensions of eigenspaces cannot exceed the dimension of the vector space and so on and so on. So they're kind of basic list of inequalities for the dimensions of eigenspaces, how they're related to the dimension of the total space. Please have a look at the lecture notes. Okay, so question 5. So let's see B, an invertible linear operator prove that on the finite dimensional vector space, prove that if T is diagonalizable, then so is T minus 1. Okay, so let me bright space, right? Because sometimes you can find solutions there to your questions. So please don't look at solutions in Google or some other websites, but rather look in the bright space. That's very important. Okay. And this is not considered as cheating, right? Okay. So please be careful. Yeah, that's fine. Okay. Please have a look at the bright space. I don't know why some students just try to Google it, because sometimes if you just look at what is posted on the bright space, you'll find all answers to your questions. Okay. Okay, good. However, let me just stress that in the written, so on the bright space, you will find a very detailed hints, but still, I mean, what I would like to ask you when you will write down the solutions, please expand them. Please expand them. So don't just copy them word by word, right? Just explain, I mean, because there could be definitely some explanation added, and please do it. Okay. So maybe the last question. Right, okay. Let me do the last question. If B is invertible, then there exists certain scalar C, complex scalar, such that A plus CB is invertible. Is not invertible, sorry, it's not invertible. Okay, so here if you look at the solutions at the hints on the bright space, you will see that the trick is you take this matrix, okay, and then so there's this C, right? There's this C. So it's kind of parameter that you would like sort of to find, right? So indeed, you may think about the C as a variable. So maybe if for you it will be easy, instead of C, you can put lambda. That's maybe a little bit easier. And then, well, the ideas would be how, so you need to relate this expression A plus lambda beta to what? To characteristic, to this matrix, you remember this, A minus lambda times the identity. And then look at the determinant, look at the characteristic polynomial. So the trick is, if you want to relate it with a characteristic expression, you want to kill this B. You want to kill this, right? In some sense. How do you kill this? Well, what we can do, we can just multiply it by the inverse of B. Look, B is invertible, so there exists an inverse, right? So for instance, what we can do, we can just multiply this by the inverse, okay? So let's just multiply this expression by the inverse. Then what do we get? We get clearly AB minus 1 plus lambda, and then we get the identity matrix. So now this is very close to the characteristic expression, right? And well, indeed, if you wish, we can multiply not by the inverse of b, but just to be just on the safe side. We can even multiply by the minus inverse of b. Well, in this way, it will be just minus minus, right? Well, let's just look at this expression. And then we see that, okay, so if say we set M to be this matrix, then our expression becomes M minus lambda IN. And this is really the characteristic expression. Yes, so we can look at its determinant. Yes. And then what do we see here? Well, we see that okay, so we see that this determinant will have a root, right? Has a complex root always. Okay, let me maybe elaborate a little bit more on this. So there's the following fact that probably you have seen in one of the first year classes. I guess it's it maybe was even explained in the first year linear algebra. So basically this fact is telling that each polynomial has a complex root. Okay, does everyone knows about it? Okay, so for instance, if I look at this polynomial, it does not have any real root, right? There is no solutions of that over real numbers. However, over the complex numbers, yes, there is a solution. So it has a root over complex numbers. And this fact holds for any polynomial. You can take any polynomial, then they're always here. If you have one eigenspace and another eigenspace, you have one vector and another one. They're non-zero, of course, right? Then, well, v1, v2 are independent. Indeed, this holds for any sets. I mean, you can take, say, you can take a linearly independent set in E lambda 1, linearly independent set in E lambda 2. Then if you combine them together, the resulting set will be again linearly independent. Yes, exactly, right. This is the theorem about linearly independent subsets from eigenspaces. Yes, that's it. Well, in that case, you just take a set consisting of one vector, right? Subset consisting of one vector. Okay, there's some more questions. Is there more questions? Yeah, what I wanted to say, I wanted to make some comments on the very last. Okay, let me still make this comment on the very last question 6.2. So there's a question asking, find a matrix, a non-zero matrix such that both A and A plus CB are invertible. Okay, for all C. Okay, good. And so again, since this is a question about produce an example or say, well, whatever shows, well, I mean, all these sort of questions, produce an example, produce a counter example, produce some explicit, I don't know, whatever, demonstration, etc., etc. Well, remember that to produce any example, the first thing one should do is to use numbers zeros and ones. Okay, Okay, so you first use zeros. If your example doesn't work with zeros, then you add 1 1. If it doesn't work, you take 2 ones somewhere and so on. Okay. Unfortunately, if it doesn't work for zeros and ones, then the next level would be to put into the game -1. Okay. And well, in this case, since we are dealing with 2 by 2 matrices, there are not so many options. I mean, look, if you have 2 by 2 matrix and you are, say, thinking about only writing them down using zeros and ones, that's pretty easy to do, right? Yes, because there are not so many options. There are not so many matrices consisting of zeros and ones. Just play around with such matrices, and then you will get immediately an example. And this, by the way, indeed is given in the written solutions on the Brightspace. Okay, good. Is there more question? Other question? Okay, let me also stress that you, of course, please ask questions. All your questions, if it contains any kind of private information, it will be cut it off from the video recording, right? So this will not be inside the video recording. Okay, so be aware.